Hello everyone, welcome to IIT and GATE classes. This is lecture 15 on operating system, and in this lecture we are going to start new topic, that is paging. Okay, it is very important topic and many times questions have been asked from this topic. Okay, first of all you should know that it is a type of non-contiguous memory allocation technique. Okay, non-contiguous non-contiguous memory management technique. Okay, non-contiguous memory management technique. Okay, so word by word we will try to understand what is non-contiguous. Non-contiguous means, for example, say this is our main memory or RAM. Okay, and here we have a process. Okay, and we want to store this process in main memory. Let us suppose size of the process is say 5 KB. Okay, and main memory, for example, see this is occupied, only 1 KB space is here, and then this part is occupied, and here 1 KB space is there, this is occupied, and here let us suppose 4 KB space is there. Are you getting it? So this is our main memory, that is RAM. Now some small part is occupied and then 1 KB free space is there, then some occupied and then 1 KB space, and then some space is occupied and then 4 KB space is there. So obviously I cannot store this process of 5 KB in this memory. Why? Because we want contiguous memory now. When we in RAM, if we have contiguous memory, then we can store it. But now we do not have contiguous memory, but total amount of memory available is okay with us. That means we have total 6 KB free memory, 6 KB RAM is available. Okay, and process size is only 5 KB, but it is not contiguous in nature. That means it is not continuously available, so we cannot store it. Okay, but paging will allow us to do that. Okay, so that is the basic meaning of non-contiguous. Okay, so what we will do, so we will divide the process into fixed and equal size parts called pages, and these pages will be stored in main memory. Okay, so wherever we have a space we can store them. For example, this page is of 1 KB, so I will store here 1 KB page. This page is 1 KB, say we will store here. Okay, and let us suppose here we have say we will divide this memory into 1 KB. I'm just giving you the idea. It is not exact technique. I'm just giving you the idea that what do you mean by non-contiguous. Okay, yeah, and here we have some space, so I will store 1 KB parts here. So now we obviously we do not remember where the first part go, where the second part go, and so on. So for that we have page map table. So page map table will keep record of which page goes to which part of main memory. Okay, so I have just given you idea what is paging. So paging is non-contiguous memory management technique. Okay, and in this technique what we are doing is we are dividing the process into fixed and equal size parts called pages, and depending upon the space these pages will be stored somewhere in the main memory, and more technically we will call them as frame. Okay, so now let me tell you the exact scenario. Take the snapshot. I will jump to the next slide. In the next slide I will tell you what exactly is paging. Yes, so I hope you have taken it. Yes, so what we are doing is, so main memory is divided into fixed and equal size parts called frames. Okay, main memory is divided into fixed and equal size parts called frames, and the process which is going to come in main memory, that is also divided into fixed and equal size parts called pages. Okay, each part is known as page, and here in main memory each part is known as frame. So this is logical division. It is not like that we have built a wall here and we have built a wall here. It is not like that. It is just logical division. Okay, so main memory is divided into fixed and equal size parts called frame. Process is also divided into fixed and equal size parts called pages, and depending upon the space, so for example this page go here, this page go here. Okay, this page go here, depending upon the space or availability, this page go here, and so on. So now we do not remember where the page has gone. Okay, which page has gone in which frame. Okay, which page has gone in which frame we do not remember. So for that we have page map table. So page map table will keep record of which page is stored in which frame. Okay, so it's just like that. You have say 3 almiras in your home, rather 4 almiras in your home, and none of the almirah is having space to occupy 4 shirts. You have 4 pack of 4 shirts. Okay, and none of the almirah is having a space to occupy these 4 shirts as it is. So you will break the packing. Okay, one shirt you keep in each almirah. Okay, and you do not know which shirt go to which almirah, so you will keep a record on page saying that your red color shirt is in almirah 1, blue color shirt is in almirah 2, and so on. Okay, so that is page map table. So this page, you can say whatever you have stored on the slip of paper, that is your page map table. Okay, and the pack of 4 shirts, that is your process, and the almirahs, that is nothing but your frames of main memory. So I hope you have got idea how exactly or what exactly is paging. Okay, so just to revise one more time, but if you want to write down the notes, you can write down that main memory is divided into fixed and equal size parts called frame. Let me write the keywords only because they are very important. You will get confused. Okay, so main memory is divided into fixed and equal size parts called frames. Okay, so in main memory we have frames. Similarly, whatever process is going to come in main memory, that is also divided into fixed and equal size parts called pages. Okay, so main memory is divided into fixed and equal size part called frame. Process is divided into fixed and equal size parts called pages. And obviously, to properly implement the scheme, page size must be equal to frame size. Okay, page size must be equal to frame size. Okay, that is the basic meaning here. Okay, so now we have to keep record of which page goes to which frame. So for that we have page map table. So you can write down. I'm not writing just to save the time. To keep record which page goes to which frame, we have page map table. You can write down properly. Okay, yes, and obviously you have come to know that each process will have its own page map table. Okay, so if we have say 10 processes in main memory, so each and every process will have its own page map table. It is also very important point. Please write down, each process has its own page map table. Each process has its own page map table. Okay. Now I will take a small numerical so that you get more clarity. I will take a very simple numerical. Okay, so let us suppose my process size is just 16 bytes. Okay, main memory is of 32 bytes. Okay, I'm just assuming it. Okay, page size is 4 bytes technically, or you can say more precisely, these are very less size, but we are just taking it just for the sake of simplicity. So process size is 16 byte, main memory size is 32 byte, page size is 4 bytes. Okay, yeah. So now let us build these bytes. Okay, so that we get more clarity. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, so since it is of 16 bytes, so we have made 16 bytes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, one more is left out. 16. Okay, so these are 16 bytes of your process. Okay, and since they are these bytes, we can fill any data here in 8 bits. 1 byte is 8 bits now, so you can take here, so 10 whatever may be the data here, so you have kept this data. But our main concentration is not on data. Our main concentration is on address. So please let me know what will be the address of the first. So you will take it as 4 zeros. 0, then 0001, then 0010, 0011. Okay, then 0100, then 0101. I think you already know these are very basic things. 0111, 1000, 1001, 1010, 1011. Then 1100, 1101, 3 times 10 and 4 times 1. Okay, so from 4 zeros to 4 1, we have made these addresses. Okay, our main concentration is here. Okay, and main memory is of 32 bytes, so it will be divided into so sorry, main memory is of 32 bytes. So let us first build the 32 bytes. Okay, so obviously it will be quite difficult for me to make it, so I will make it logically. Okay, so let us suppose 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay, then 28, then 29, 30, 31. Okay, so I think you have got it. This is 32. Okay, so how we will keep the addresses? So just for the sake of completion, I will copy this out. Okay, yes. So uh, just a second. I think it is not dragging properly. Yeah, actually, it will waste our time. Why? Because the you can say spacing is not proper. Okay, so just leave it. Okay, just leave it. So accordingly, we will number it. Okay, so you have got the basic idea that it will be say 5 times 0, 1, 2, 3, 4, 5, and then 0, 0, 0, 0, 1, and so on till 1, 2, 3, 4, 5, 5 ones. Okay, yeah, so it is very basic. I think you already know. So 32 bytes means from 5 zeros to 5 ones. Okay, we will take the addresses. So I'm not filling it just for the sake of completion, or you can say just for the sake of simplicity. I'm not filling each and every address. You can fill it yourself. Okay, and now next is page size is 4 bytes. Page size 4 byte means so 1, 2, 3, 4. So this is 4 bytes. So this is first page. You can consider it as page number 1, first page. Now 1, 2, 3, 4, 4 bytes. So this is now page number 2. Next 1, 2, 3, 4. This is page number 3. Okay, this is page number 3, and last is page number 4. Okay, I think you have got it. So now accordingly, see, let us suppose our first page goes to somewhere. So let us take say this is okay. So actually I just want to fill the values, but it will waste our time. So okay, let me do it. 1, 2, 3, 4. So this is your frame number 1. Okay, please let me know these facts. So the CPU. Okay, so let me build here. So this is a CPU. Okay, and I will do these things also. Please don't worry. So very first thing is there are 4 pages for the process. Why 4 pages? Because page size is 4 bytes, process size is 16 bytes. 16 divided by 4, that is 4. So there are 4 pages like this. Okay, and main memory is of 32 bytes. So how many frames will be there? Obviously page size and frame size are equal. So 32 divided by 4, that is 8. So there are total 8 frames. Okay, so I am just labeling them. First frame, then 1, 2, 3, 4. Second frame, then 1, 2, 3, 4. Third, 1, 2, 3, 1, 2, 3, 4. Fourth, 4. Fifth, 1, 2, 3, 4. Sixth, 1, 2, 3, 4. Seventh, and then 1, 2, 3, 4. Okay, so I think there is some mistake. 1, 2, 3, 4. Then okay, 1, 2, 3, 4. Okay, 1, 2, 3, 4. Okay, 1, 2, 3, 4. Okay, 2, 3, 4. Okay, 1, 2, 3, 4. Okay, 1, 2, 3, 4. Okay, 1, 2, 3, 4. Yes, so last one I have to delete. No problem. I will simply delete this. So these are the 32 bytes. Okay, so how, see this. Now I will simply say there are 4 pages. So how you will label each page, or how many bits are needed? Obviously 2 bits are needed. So 0, this is page number 0, 0, then 0, 1, then 1, 0, and then 1, 1. Obviously you will label like this. Okay, and from address, how you will point out? I will say like this. See this, first 2 bits are 0. See this. Okay, First two bits are 0. Then 0, 1. You can check it out yourself. 0, 1. Then 1, 0. Okay. And then 1, 1. So I hope you have got it. So 0, 0, 0, 1, 1, 0, 1, 1. And since there are 8 frames in main memory, so how you will label them? From 000 to 111. Okay. So, okay, just I will label it 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1. Okay. Huh. So I will label it as 3 times 0, then 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, yeah. And you can check it out yourself. First three bits will be 0 here. Okay, and next address will be what? 0, 0, 1 double 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, triple 1. Okay, so here it will be first three bits will be 001. You can check it out yourself. Okay, so you can check it out yourself. So this is, I think, a very simple way. Hmm. Yeah, so I hope you are getting it. So what are this? So this is what your page number. This is page number, page number, page number. Okay, so these are what frame number, frame number, frame number. These all are frame numbers. Okay, so now let us assume our first, you can say, page goes here. Okay, so first page goes here. Let us suppose this. Okay, second page goes here. I'm just assuming it. Third page goes here. And let us suppose fourth page goes here. Okay, so now I have to keep record now which page goes to which frame. So for that I have told you we have page map table. So first of all, please let me know how many entries will be there in page map table. Obviously the number of pages of the process. So there are 4 pages of the process. So there will be 4 entries in page map table. Okay, and each entry will contain what? It will simply contain the frame number. So for example, first page goes here. So I will keep here 010. Second page goes here 001. Third page goes 011. Oops, sorry. Third page goes to 111. And fourth page goes to 011. Okay, so these are the 4 entries in page map table. This is your page map table. Okay, yeah, and now see what we are going to do. Now see properly. So for first of all, you should know CPU will generate logical address. Okay, CPU. Let me jump to the next slide. I will tell you these facts. Take the snapshot, or do not take it. I will just give you the time after completion. Okay, so now the basic fact is that CPU will always generate logical address. CPU will always generate logical address. Okay, logical address. Logical address means the byte number of process which CPU wants to access. Okay, whatever byte number CPU wants to access, that is given by CPU. So CPU does not know anything. This is all hidden to CPU. Okay, so yeah, you have done, your rather operating system has done this just so that process can be kept in main memory. Okay, so you have just created a process will be in hard disk, and now we want to store this process in main memory. So for that, OS has done all these things. CPU does not know anything about this, so that what exactly has happened, or where the process has been stored, and all. CPU does not know anything. CPU simply want byte number. For example, CPU want to access, say CPU has generated address, say 0 0 1 00. Okay, so what do you mean by this? CPU has generated by because CPU generated address is logical address. Logical address is the byte number of the process which CPU wants to access. So for example, CPU generated this, so that means it want to access fifth byte. counting from 0. Please see this, counting from 0. So first byte, second byte, third byte, fourth byte, fifth byte. So CPU wants to access this fifth byte. Okay, that's why CPU has generated this. Now, this fifth byte actually where it is stored? It is stored here. Are you getting it? And please see this. So this entire you can say page is stored in main memory as it is. Okay. So what we want is, so we want to access this. So where it has been stored? 001 it has been stored. So what I will say, so basically what we are going to do is CPU generated address, that is logical address. I have told you, no, CPU always generate logical address. So this logical address is divided into two parts. LA is divided into two parts. What are these two parts? P and D. P is page number and D is offset. Offset within page. Okay, that means which byte you CPU wants to access. So this is the page number. That means what page number CPU want to access, and this is the byte number. That means within page which byte it wants to access. For example, see this, CPU generated address is divided into two parts. So I will divide it like this, 01 and 00. Okay, so why? Because page number I have told you 0001 1011. So these are the page numbers. So CPU generated address is divided into two parts. So first part is the page number and this is the byte number. So it will, so CPU is saying that please give me 01 means second page. Na? This is first page, this is second page. So second page 00 means first byte. Second page, first byte CPU wants to access. Like this you will reach. So here also you will say second page, this is the first page, second page, first byte. It want to access this, it want to access. Are you getting it? So CPU generated address, that is logical address, is divided into two parts, P and D. So P means which page number, and in page, within page which byte number it want to access. So this means that page number 1, that means second page first byte it wants to access. Let me give you another example so that you get more clarity. For example, 1011. So this means what? This is page number, this is offset. So page number is 10. So 0001 10 means third page, and this means what? Double one means fourth, because counting start from 0. So I will say third page, fourth byte it wants to access. So you can check it out yourself. First page, second page, third page, fourth byte CPU wants to access. 1011 is the address. Okay, so I hope you have got it. So this is page number and offset. Okay, yeah, so CPU generated address, that is logical address, is divided into two parts, that is page number and offset. Okay, and now what we are going to do is, so for example, this is 01 na? So 01 means you have skipped one page. Okay, so one, you take this as decimal 1. So you will skip one page. That means next is your page. Okay, so you will take the entry. So CPU will, so now what we will do, so this page number will be replaced by this frame number. These are the frame numbers na, which we have kept. What is this page map table? Simply tell me. This page map table is storing that which page of a process goes to which frame in main memory. So you have just kept 001 here. So I will simply replace 01 with 001. Okay, and then 00. This 00 will be copy pasted as it is. Okay, yeah, so finally we have got, this is known as physical address. So physical address means logical address is the address generated by CPU, that means byte number of process which which CPU wants to access. Physical address means the actual address where that byte is stored. So this is the physical address or actual address where that byte is stored. So 0100, see this, you can check it out yourself. It is stored in 0100, it is stored in 00100. Here you have stored it. Okay, so this same byte number is stored here. Okay, so I hope you have got it. So this is the physical address. Now you can take another example. Okay, then I will make a diagram properly. So if this 1011, so you will say 1010 means what? 2. So you will skip two entries in the page map table, and the third entry will be yours. So you will keep, so 10 will be replaced by 111, and this 11 will be kept as it is. And here I will say that this is the physical address where my byte is stored. So you can check it out yourself. 1011. See this. This was this. So this you can say page is stored here, na? So you will say last one. Okay. So here also last. So obviously here also last. Okay. So here is this is the physical address where your byte is stored. So I hope you have got it. And what is the address? So 111. So you will say 11100. So for this 00, then 01, then 10, then 11. So here we will keep 111, 111, 111. So 5 times 1 is the physical address. Okay, so I hope you have got it. So you can take snapshot of this, and in the next slide I will tell you the proper logical diagram of the paging. So I hope you have taken the snapshot. Okay, so I think you have got it. Physical address is the where or the actual address where that byte is stored. Logical address is the address generated by CPU, and which is simply saying that where actually, or you can say the byte number. Okay, a logical address is the address generated by CPU. That means the byte number which CPU wants to access. Okay, and CPU does not know anything about paging and all. CPU will simply generate the byte number which it want to access, and then this byte number, we can say this logical address will be divided into two parts, P and D. Okay, this P will keep will help in locating the page map table where which entry we have to access, and after accessing the entry we will replace this P by the frame number, and this offset will be copy pasted as it is, and then we will get a physical address. From that we will access the main memory. Okay, so don't worry if you are not getting it, please rewind the video, watch it again and again, you will get more clarity. Take the snapshot. I will jump to the next slide. Okay, so now I will tell you the basic scheme. Okay, so CPU generated address, that is logical address, is divided into two parts, P and D. This P we will access the page map table. Okay, from the page map table, what we will say. So since it is P now, so you will skip P entries. The next entry will be yours. So for example, here we have F. So this F will be P will be replaced by F. This D will be kept as it is. We will go to main memory, and this will be the physical address. Okay, physical address of main memory where that byte is present, and this is the logical address, PD. PD is the logical address, and this is the physical address, and this is the page map table. Okay, so P entry we will skip, and after that we have the entry F. So we will replace, we will get F, and then this D will be copy pasted after F, and we will get a physical address. Okay, and we will go and access the main memory. So I hope you have got, this is the basic scheme of your paging. Okay, so now from here we will try to derive few formulas. Okay, or and I will tell you that what type of questions will be asked in GATE regarding this. Okay, yeah, so let me jump to the next slide, take the snapshot. So I will write one by one all the questions. So assume process size is 16 bytes. Same numerical I am just taking. Okay, so that you get more clarity. This 16 byte process. Okay, process size is 16 byte. Main memory size is 32 bytes. Okay, and page size is 4 bytes. Whatever data we have taken, I am just taking that just for the sake of simplicity. And now I will answer few questions. So question number one. Question number one is size of logical address, size of LA. Question number two, size of PA, that means physical address. Question number three, number of entries in page map table. Question number four, size of page number, size of page number in logical address. Question number five, size of offset, size of offset in physical address. Okay. Question number six, size of PMT. And question number seven is number of bits for frame number in, number of bits for frame number in physical address. Okay. Okay. So let me tell you that one by one. What is the size of logical address? That means CPU will generate the number of bits in address whichever is generated by CPU. So that will be, obviously CPU does not know anything. It will simply say the byte number which it want to access for the process. So process is of 16 bytes. So I will simply say log base 216. Okay, that is 4 bits are needed. I think you already know if we have 16 objects, so how many bits will be needed to label these 16 objects? So obviously 4 zeros to 4 1. So forget about it. You just say me if you have two objects. Okay, so these objects can be anything. So how many bits you need? Only one bit, 0 and 1. You will label them. 4 objects, 0 0 0 1 1 0 1 1. So 2 bits are needed. So how you are getting it? Log base 2 4. How you are getting 1? Log base 2 2. So for if 16 bytes, then you will say log base 2 16, that is 4 bits. Next is size of physical address. So main memory is of 32 bits. So obviously how many bits are needed to label each byte of main memory? 32 byte, na? So log base 2 32. That will be 5 bits. You can check it out yourself. See this 4 bit was the logical address. Logical address 4 bit and physical address is of 5 bits. You can check it out yourself. Okay. Yes. Next, number of entries in page map table. How many entries will be there? That is obvious. Number of pages. For each and every page, we have entry in the page map table. For each and every page, we have entry in the page map table. So how many pages are there? That is very obvious. Page size is process size is 16 bytes. Page size is 4 bytes. So 16 divided by 4, that is 4. 4 is the entries in the page map table. Okay. Yes. Size of page number in logical address. So obviously in logical address, page number, see this, I have divided into two parts, na? Page number and offset. Logical address was divided into two parts, page number and offset. So how many bits for page number? That is very obvious. That means, see this, we have got 4 pages, na? Okay, we have got 4 pages. So to label 4 pages, how many bits are needed? That is log base 2 4. So I will simply say answer will be log base 2 4. That is 2. Okay, don't worry, I will tell you generalized formula after this. Okay. So size of page number in logical address, so that means number of pages are 16 by 4, that is 4. So you will take log base 2, you will get 2. Size of offset in physical address. Offset, so this is the offset, na? This offset was copy pasted. Are you able to remember it? See this, P was replaced by F from the page map table. Since it was P, so you have skipped P entries. Next entry was yours. So you have got F. So this F, okay, and this D was copy pasted now. So this is the offset. Okay. So what will be the offset? So obviously page size. So if page size is 4 bytes, so you have taken 2 bits. See this. Everywhere 00011011. Again here 00011011. 00011011. Here also 00011011. Last 2 bits you check. Okay, so why 2 bits are needed? Because page size was of 4 bits. Since page size is of 4 bits, so we need only 2 bits. So that means what? Log base 2 page size. Okay, so again here answer will be log base 2 4, that is 2. And this is obvious, size of offset in physical address, or you can say logical address, because offset size is same in both physical as well as logical. Okay. Next is size of page map table. Size of page map table will be what? Obviously number of entries multiplied by size of each entry. Okay, that will be size of PMT. See this. So PMT, if you check, size, the number of entries, there are 4, and size of each entry is 3. So 4 into 3, that is 12. And how you have got it? So number of entries are 4. Why number of entries are 4? Because number of pages are 4. Okay, and how entry size is 3? Because frame number, please check it out yourself. Frame number is of 3 bits. Okay, that's why entry is 3. Okay, yes. So number of entries are 4. Size of entry is 3. So 12 bits. Very obvious. Number of bits for frame number in physical address. So number of bits for frame number, that is nothing but your size of each entry, that is 3 bits. Okay, and how you have got number of bits for frame number in physical address? See, you simply divide main memory divided by page size, or page size and frame size are equal, na? So main memory size divided by frame size, you will get what? Number of frames. And to label each frame, we need bits. So log base 2 will be our answer. That means 3 bits. Okay. So number of bits for frame number in physical address, and that is size of entry in page map table. One and the same thing only. Okay. And they are giving us 3 bits. Okay. Yes. So now I will tell you generalized formula for each and everything. Okay. So now let me give you the generalized formula for first. size of logical address. How you are going to calculate size of logical address? That will be log base to log base to process size. Okay. Next, size of physical address, log base to main memory size. Next, number of entries in PMT, process size divided by page size. Okay, because it will give us number of pages. Process size divided by page size, that is number of pages, and for each page we have one entry in page map table. So process size upon page size. Size of page number in logical address, the size of page number, that will be this quantity, whatever we have got. You just do log base 2 because number of pages are now with us. So log base 2 number of pages, that will give us our answer. So what will be our answer? Log base 2 process size upon page size. Next, size of offset in physical address. Offset is very simple. You will say log base 2 page size. Okay, so whatever is the size of the page, you just do log base 2, you will get offset in physical address or logical address, size of offset. Okay, so for example, here you are having say 2 bits now, so that's why why 2 bits, because page size was of 4 bytes. Page size was of 4 bytes. So to label 4 bytes, we need only 2 bits. Log base 2 4, that means 00011011 00011011 and so on. So I think you have got it. Okay, next, size of page map table, number of entries into size of each entry. So how you will find number of entries? Number of entries is this, process size divided by page size multiplied by size of each entry. What is the size of each entry? That is nothing but number of bits for frame number in physical address. So how you will get it? Log base 2 main memory size divided by frame size. Okay, so you just multiply them, you will get the answer. Okay, yeah. And what is the number of bits for frame number in physical address? That is very simple. Number of bits for frame number will be what? Main memory size divided by frame size, number of bits needed, so log base 2. So that is our answer. Okay, so this and this are same here. Okay, so I hope you have got the entire idea about how exactly paging is done. Okay, so I think there is no problem with any of you. So now I will try to solve few numericals so that you get more clarity. Take the snapshot of this. I will jump to the next slide. Hmm. So similar type of question we will try to solve. So we will say process size. Process size is 32 KB. Main memory size 512 KB. Page size is 2 KB. And we will try to find all these things: size of logical address, size of physical address, and so on. Okay, let me copy it out if I am able to do it, but no, it will create problem for us. Okay, so one by one we will solve. Okay, yeah. Question number 1. What is the question number 1? Size of logical address. Logical address size, how you will calculate? From the process size. So log base to 32 KB. Okay, so how you will write 32 KB? So you should know this fact. Okay, 1 KB 2 power 10, 1 MB 2 power 20, 1 GB 2 power 30, 1 TB 2 power 40. Okay, 32 KB you are saying. 1 KB is 2 power 10, 32 is 2 power 5. So you will say simply 2 power 15. So this and this got cancelled, 15 bits. Next, next question is size of physical address. Log base to main memory size. Main memory size is 2 power 19. So you will simply say 19 bit. Okay, question number 3. Number of entries in page map table. Number of entries. Number of entries will be what? Process size upon page size. Okay, what is the process size? 30. Now please do not try to do calculations and all. You simply do this thing, whatever I will tell you. Please focus here. Process size is, you write it in 2 power into power format, 2 power 15. Page size is 2 power 11. I think you have got it now. 1 KB is 2 power 10, 2 power into 2. So that means 2 power 11. 2 power 4, that is 16. Okay, so number of entries will be 16. Next, size of page number in logical address. Size of page number in logical address. So that means number of pages you want to find. Okay, so number of pages will be what? Process size upon page size, that is 16. You have got it. Na? Number of pages 16. So log base 2, just do it. So log base 2 16, that is 4. Okay. Question number 5. Size of offset in PA or LA. That will be nothing but log base to page size. So log base to 2 power 11, it will be cancelled 11 bits. Next, a size of page map table. Size of page map table. Number of entries multiplied by size of each entry. How many entries will be there? Number of pages. So number of pages are 16. So 16 entries. Size of each entry, log base 2. Main memory size. Main memory size is 512 KB. Na? So 2 power 19 divided by page size or frame size. One and the same thing. Na? Page size or frame size 2 KB. So 2 power 11. So it comes out to be 16 multiplied by it will be 8. Okay, so answer will be 8. So 16 into 8 is our answer. I think you have got it, na? 2 log base 2 and 2 got cancelled. 8 we will get. So 16 into 8. Now you are not able to solve. Don't worry. You will simply say 2 power 4 into 2 power 3. That is 2 power 7. That is nothing but 128 is our answer. Okay, if you do not know calculation, you can do it very easily. So 128 is our answer. Question number 7. Number of bits for frame number in physical address. Number of bits for frame number. So similarly, I think you have got it. Na? 8 is our answer. I should not waste time here. It is very simple. Okay, because size of each entry is nothing but number of bits for frame number. Okay, and if you have still any doubt, what you will say, mean memory size 2 power 19. Frame size is 2 power 11. So 2 power 8. So there are total 2 power 8 frames. To label 2 power 8 frames, how many bits are needed? 8 bits are needed. You simply take it log base 2 power 8. So log base 2 will be cancelled. 8 is our answer. So similarly, 8 we have got it. So I hope you have got the point. You can take this snapshot. I will jump to the next slide now. Okay. So now we will try to solve another bit, you can say difficult kind of question. Difficult, it is actually not difficult. It's just for the sake of completion so that you get more clarity. Main memory size is 4 GB. Process size 512 MB. Page size 256 KB. Okay. And then we will try to solve we will find all the questions. So question number 1. Size of logical address. Size of logic. So okay, one more thing, since it is in GB, it is in MB, it is in KB. So batteries, you just make it in power of 2 so that you get more clarity. So it will be 2 power 32. I have just told you GB is 2 power 30 and 4 means 2 power 2. So 2 power 32. It will 5 and 2 is 2 power 9. You can check it out yourself. 5 and 2 is 2 power 9. MB is 2 power 20. So 29. So 256 is 2 power 8. KB is 10. So 2 power 18. So now everything will be very, very easy now. Okay. So first is size of logical address. Logical address size will be what? Process size, log base to process size. So it will be simply 29. Next is main memory size of physical address. Physical address size will be what? 32 bits. Log base to 2 power 32. See this. Log base to 2 power 32. This will be cancelled. 32 is our answer. That's it. Question number 3. Number of entries in page map table. Number of entries. What is the number of entries? Number of each, one entry for each page. So how many pages will be there? Process size divided by page size. So 2 power 29 divided by 2 power 18. What will be our answer now? 2 power 11. 2 power 11 is 2048. So 2048 entries in page map table. I think you have got it. Okay. Next, size of page number in logical address. Size of page number in logical address. So directly indirectly we want to find, see, number of pages. How many pages will be there? Number of pages will be the 2048. Okay, and page number. Okay, so in logical address page number will be of 11. 11 is log base 2, just do it. Okay, so I will simply tell you, see this. Logical address is of 29 bits. So first 11 bits will be for page number, and last, how many? 29 minus 11, 8, and 18 bits is for offset. Okay, so 11 plus 18, we will get 29 bits. Okay. So I have just got 11. So I think nobody is having any confusion. Size of page number in logical address. That means number of pages. You just find out number of pages and log base 2. You just do log base 2 because we want bits. Okay, we want bits. So it will be 11. So 2 power 11 pages are there. So to label 2 power 11 pages, we need 11 bits. Question number 5. What is question number 5? Size of offset in physical address. Size of offset in physical address. So obviously offset, I think we have got it 18. We have directly got it, but another way can be log base to page size. Page size is 2 power 18. So finally we will get 18. Okay. I think you have got it. Question number 6. Size of PMT. Size of PMT. How you will find size of PMT? And number of entries multiplied by size of each entry. How many entries are there? Entries I have already find out 2048. Size of each entry. Size of each entry will be log base to main memory size divided by page size. So what it will be? 2 power 4, 14. 2 power 14. So finally we will get 14 as the answer. So 2048 into 14 bits. This is my answer. So I hope you have got it, how we have calculated it. Size of entry will be frame number. Na? So how many frames are there? So you can find out number of frames will be main memory size divided by frame size, because page size and frame size are equal. So 2 power 32 divided by 2 power 18, 32. Why 2 power 32? See this. I have just told you main memory size is 4 GB. Na? That's why. So 2 power 32 divided by 2 power 18, it comes out to be 2 power 14. So 2 power 14 are the number of frames. To label these 2 power 14 frames, we need only 14 bits. So that's why 14. So question number 7 is frame number. No? I think number of bits for frame number. Number of bits for frame number is same. That is 14. Okay. So now by solving these numericals, I think you have got crystal clarity that how you will approach the paging. Okay. So let me jump to the next slide and solve few more questions. Take the snapshot. Okay. Next another type of question I'm telling you. See, they are saying size of logical address is 16 bits. Okay. And process has 16 pages. Process has 16 pages. And now they are saying find size of each page. Very simple. Logical address is of 16 bits. Okay. So total these are 16 bits. Divided it into two parts P and D. So process has 16 pages. 16 pages means what? P. In logical address P will be what? Log base 216, that is 4. So it will be of 4 bits. I think you have got it. Now 16 pages are there. To label each page, how many bits will be needed? Only 4 bits will be needed. Okay, and now you calculate the D part. So what will be the D part? 16 minus 4, that is 12. So I think you have got it now. Total is 16. Total is 16. 4 you will subtract, so you will get 12. So offset is of 12 bits. So they are what saying? Size of each page. So obviously very simple. Size of each page will be what? 2 power 12. 12 bits are needed to label the bytes in the page. So how many bytes will be there? Obviously 2 power 12. Just reverse it. So 2 power 12 is nothing but 4 KB. Okay. So size will be 4 KB, or you can say 4096 bytes. Okay, I think you have got it. I have just converted into that. Okay, so what I have done it, 4 KB means 4 into 2 power 10. 1 KB is 2 power 10. 2 power 10 is 1024. So 4 into 1024, that is nothing but 4096. Okay, yeah, take the snapshot. I will jump to the next slide. Hmm. Another question. Physical address is of 18 bits. Okay, physical address is of 18 bits. Frame size is 256 bytes. Okay, and they want to find size of entry. Size of entry of page map table. Okay, so it is again very simple. Physical address is of 18 bits. So these are the total 18 bits. So how physical address is divided? It is divided into two parts, frame number and offset within frame. So they are saying frame size is 256 bytes. So 256 bytes means what? How many bits will be needed to label these 256 bytes? 2 power 8. That means 8 bits will be needed. Okay. 256 is 2 power 8, na? So it's just simple. See this. Either you do log base to 256. So you will get the answer. But I will simply say log base to 2 power 8. Na? So it will be cancelled. 8 is our answer. So directly and directly, I will simply say 256 is 2 power 8. So just take 8. 8 is your answer. So this 8 is this offset. So how many are left out for the frame number? Total is 18. This is 8. So how many are left out? 10. Okay. So that is our answer. Okay. So 10 bits. So 10 bits are needed to label the frame number. Okay. And they are saying what size of entry of PMT. So size of entry of PMT will be 10 bits. Okay. So I hope you have got it. Okay. It is very simple. Take the snapshot. I will jump to the next slide. Okay, yeah. And one more way is coming to my mind. Let me tell you that also. Another way is, since physical address is of 18 bits, so I can simply reverse this. Let me take another color. So this green color means second way to solve this question. Physical address is of 18 bits. So you will say main memory size is 2 power 18. I think you have got it. Just reverse it. Frame size is 256 bytes. So frame size is 256. That means 2 power 8 bytes. So size of entry means you just want to find number of frames. So number of frames will be what? Main memory size divided by frame size. 2 power 18 divided by 2 power 8, you will get 2 power 10. So number of frames are 2 power 10 and we need number of bits needed. So that will be 10 bits only. And this is what we have got it here. Okay, so there are many ways to solve questions. Okay, whatever way suits you, you can take that. According to me, this was very easy. Okay, yeah, take the snapshot. I will jump to the next slide now. So I hope you have taken it. Next question. Main memory size is 256 MB. Frame size, or frame number in physical address is of 8 bit. Frame number in physical address is of 8 bits. Okay. Size of each frame. They just want to find size of each frame. Again, very simple. Main memory is 256 MB. So you just reverse it, but you will get 2 power 28. Na? So I will say 28 bit is the main memory physical address size. Okay, 28 bit physical address size. Now what they are saying, frame number in physical address, they are saying of for physical address. Na, that's why I have done like this. Are you getting it? Why? From a main memory, just I see the main memory, it is of 256 MB. Then I simply said you take 28 bit physical address. Why I have you can say why I need to find physical address, just because they have said that frame number in physical address is of 8 bits. So that's why I have find out physical address. Okay, so main memory size is 256 MB. So 28 bit is the size of physical address, and frame number, I think you already know, physical address divided into two part, F and D. So frame number in physical address is of 8 bits. Okay, so 8 bits is given to this, and each then offset will be of 20 bits. Obviously, this is 28. 28 minus 8, that is 20. Now, size of each frame. What will be the size of each frame? That is very easy. 20 bit is the offset. So 2 power 20, that is 1 MB. Very simple. Okay. So I hope you have got it. Okay. Yeah. So take the snapshot. I will jump to the next slide. Next question is, if size of each entry in PMT is of 8 bit, size of entry 8 bits. Okay, find size of main memory if page size is 1 KB. Page size is 1 KB. And they want us to find size of main memory. Okay, what is size of main memory? They just want to ask like this. So what I will say, size of entry is nothing but the frame number. So frame number is of 8 bit. Page size is 1 KB. Page size is equal to the frame size. Frame size is 1 KB. That means 2 power 10. So 10 bits are needed for page size. So directly, indirectly, now I have got physical address size. Very simple question. Physical address. So size of entry is 8 bits. That is nothing but frame number. So frame number and offset within frame. So frame number is of 8 bits. And page size is 1 KB. So that means what? Offset within page or offset within frame. One and the same thing. Na? Page size, frame size, same. So 10 bits. So 8 plus 10, that is, this will be what? 18. So physical address is of 18 bits. So, and they are saying size of main memory. So 2 power 18 is my answer. 256 KB. Very simple. Okay. Take the snapshot. I will jump to the next slide. Next question. If logical address is of size 15 bits, logical address is of 15 bits. Okay. I think these slides are over. So let me take another slide first. Okay. Now it's okay. Yeah. So logical address is of size 15 bits. LA is of 15 bits. Page number is of 5 bits. Page number is of 5 bits. Find size of each page. Okay, yeah. Logical address is of 15 bits. So this is total 15 P and D. So page number is of 5 bits. So total 10 bits are for page offset. And they are just saying size of each page. So size of each page will be what? 2 power 10. That is 1 kilobyte. Or you can say 1024 bytes. Very simple. I think you have got it. Yeah. Take the snapshot. I will jump to the next slide. Next is size of PMT is 8 bytes. Size of PMT is 8 bytes. Number of entries are 4. Number of entries are 4. Page size, they are saying 2 KB. And they are saying size of main memory. Okay. So it's very easy. What we will say, size of PMT is of 8 bytes. Number of entries are 4. So directly, indirectly, what do you mean by this? Now it is very, you can say, tricky question. Try to focus here. PMT size is of 8 bytes. Number of entries are 4. So size divided by number of entries, that will give us size of entry. What will be the size of each entry? 2. What is this 2? Please try to focus here. This is 2 byte. 2 bytes, that means 16 bits. So each entry size is of 16 bits. Now page size is 2 KB, that means 2 power 11. Okay, page size is 2 KB. So obviously page size and frame size are equal. So I will simply say number of entry size of each entry is 2 power 2 bytes, that means 16 bits. Size of each entry 16 bits means what? Number of frames. Number of frames in main memory will be 2 power 16. Okay, and size of each frame is 2 power 11. So 2 power 27. That means 128 MB is the size of main memory. Okay. So I hope you have got it. If you are facing any kind of difficulty, then you have to rewind the video and watch it again and again. You will get more clarity. Very simple numerical. Size of entry. So it was the way basic twist, 2 byte entry. And everywhere entry I have taken in bits. So 2 byte means what? 16 bits. So 16-bit entry. That means what? Number of frames in main memory is 2 power 16. Now that's why 16-bit entry is there. Number of frames are 2 power 16 and size of each frame, page size and frame size are same, 2 power 11. So 2 power 16 into 2 power 11, that is 2 power 27, that is 128 MB. Very obvious. Okay. Yeah, so that's it. So here we have completed the paging topic. In the next lecture, we will start segmentation. That is also very important. Okay. Thank you so much. Bye-bye.